So here are the answers to the questions at the end of the previous chapter. Hopefully you've got all these right. So why don't you tick these off before we go on to sound waves. So what are sound waves like? Well, sound waves are longitudinal waves, which means that the oscillations are parallel to the direction of energy transfer. And they're mechanical waves because they require a medium to travel through. They need particles, for example air. They cause vibrations in the medium they're travelling through, and these vibrations are detected by the ear as sound. The pitch of a sound, whether it's high, la 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 la, or low, la 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 la, is determined by its frequency. The loudness of a sound is determined by the amplitude. Waveforms of sounds. Now, an oscilloscope is a machine that shows the compressions and rarefactions of sounds as waves on a screen. But this doesn't mean that sound waves are now transverse waves. They're longitudinal waves. It's the machine that converts it so that you can see the waveform. And this is an oscilloscope screenshot. You can see on the left this sound has a smaller amplitude, which means that the oscillations are not as great from the middle to the wave crest. And it has a smaller frequency as well. There are few of them passing a point per second. So it sounds quiet and it sounds like a deep note. The one on the right has a greater amplitude. You can see that the oscillations are greater. And it has a higher frequency. There are more waves passing a point per second. So it sounds louder and higher. And echoes are reflections of sounds. The waves can be reflected in the same way as any other waves. Okay, so quickly test yourself. Hopefully you've printed out all these notes so you can answer it now and find the answers at the beginning of the next chapter.